Hello and welcome back. So this is a very famous picture. Most of you have probably seen this picture or at least heard this story before. So you've heard of the Hindenburg disaster, right? And that was a large dirigible that they tried to fill with hydrogen gas instead of helium and then float it. Why hydrogen gas? Well, because one molecule of hydrogen gas only weighs 2 AMU. One atom of helium weighs 4 AMU. So the same amount of gas would weigh half as much when you fill it with hydrogen. And so your balloon can float even though it's smaller in size, or the same size balloon could carry more cargo. So that's why they were trying to make this one. And they're like, hey, let's just make sure that it's nice and safe. We'll put this big coating on it and everything will be good. But what happened is the dirigible got too close to some power lines, tore a hole in the side, and the reaction of H2 plus O2 goes to 2H2O. And we got to put a 2 here. That reaction is extraordinarily favorable towards water, and you're going to make water. It is explosive. It releases a ton of energy, and the Hindenburg did explode, and several people died. I don't remember how many, right? But it was a very tragic accident. Now, one interesting thing about it is I hear the word Hindenburg, and I always think about, oh, did this happen in Germany or anything like that? But does anybody know actually where this thing exploded? Well, it was in New Jersey. So the Hindenburg was actually a commuter dirigible that was commuting from a small airport in New Jersey to the main airport in New Jersey for people who wanted to take flights there. Okay, so this actually happened in the US, and I don't think most people realize that because of the name. Hindenburg doesn't sound very American, which is fine. Not everything in America has to sound American. But in any case, so this reaction happened, and it's a very, very favorable reaction, and we're used to that. That's the world running forward. I'm not going to go into all the details, but you can actually turn this into a half-cell reaction and think about it as an electrochemical reaction. If you do this, you get 2 waters plus 2 electrons goes to H2 plus 2 OH minus. And you've got 4 electrons plus 4 H plus O2 goes to 2 H2O. Liquid. If you multiply those and add those up, you end up with the top equation there. So you get the exact same reaction. But now we've turned it into an electrochemical reaction. If we look to turn it to an electrochemical reaction, we can then look up half-cell potentials. Now, the standard reduction potentials that you're going to look up in a table for these ones are about, minus 0.83 volts and 1.23 volts. But that's not going to be the ones I write down. Why? Because these cells are not at standard conditions. These are non-standard conditions. So it turns out that not only can we measure standard conditions against a standard hydrogen electrode, we can measure non-standard conditions against the hydrogen electrode as well. And so I'm going to put an E cell here, but I'm not going to put the little knot there. So E cell in this case is 0.41 volts, because the concentrations of OH minus and H plus are that of water, not 1 molar. But if you do that with those concentrations, you get E cell equals minus 0.41 volts. That's an important one. And you get the E cell is equal to 0.82 volts. So if we want to calculate the cell potential for this guy, it's going to be cathode minus anode. 82 volts minus 0.41 volts. And we get 1.23 volts positive, which is good if we want that to be spontaneous. So it turns out when you do an electrochemical type of reaction with H2 and O2 going to H2O, if you can turn it into an electrochemical reaction, you'd get electrons with 1.23 volts of energy. And again, a very, very favorable reaction. The K here, if you were to calculate it, is about 10 to the 83rd. Very, 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 very favorable reaction. But this is what the world looks like running forwards, right? We've got this reaction with a K of 10 to the 83rd. Right? That is a very favorable reaction. It's essentially going to go to completion. Can we reverse it? Can we make that reaction run backwards if we wanted to? That's hard. How do you make something with such a strong driving force in one direction and make it run backwards? So what's the world running backwards, right? You talked about the arrow of time, briefly when we talked about entropy, and you said entropy actually implies time because it says that over here we had a lower entropy, over here we had a higher entropy, and time passed in between those two things, right? And we can tell whether time passes even in just looking at some pictures of something, right? If something pours up, if we got a video and somebody goes like this and water goes up into, we know that time's running backwards because that's just not what happens, right? Gravity pulls things down and we know time running forward. Or something spontaneously that's in pieces goes and forms a nice little hole. We know that's a backwards thing because that just doesn't happen, right? And we understand that a little bit from an entropic level now, but it's pretty obvious when you're looking at some of these things. So how can I make this reaction with a K of 10 to the 23rd, 83rd, run backwards? And the answer is we can. We can make that reaction run backwards by using a process called electrolysis. Electrolysis is a very, very simple concept, but of course, maybe a little bit of detail in there about how to actually do it. But the concept of electrolysis is this. I've got this reaction. It's got a driving force in one direction. So this reaction is pushing with 1.23 volts, trying to go this way. And right, if there's not much in its way, it's going to have an easy time doing that. So what I'm going to do is I'm going to take another reaction, and I'm going to make sure that this reaction over here on this hand is stronger than this reaction in this hand. So this one's pushing with 1.23 volts. I'm going to come up against it. And I'm not even going to push with 1.23 volts. I'm going to push with 5 volts. I'm going to make it go this direction, even though it doesn't want to. It's pushing with 1.23 volts in this direction, but I'm going to say, hey, no, I'm going to push it with 5 volts in this other direction. And if I can exceed it enough, I can make this reaction run backwards. And if I do it in a very controlled fashion, I can make that actual reaction of H2 plus O2 going to water run backwards. And I can turn water into H2 and O2. They call it splitting water, and it's kind of touted as this like magic bullet for energy needs in the future. Is if you can just split water, you can then combine the water in a fuel cell. You've probably heard of fuel cell vehicles or fuel cells in general. They are taking the electrochemical reaction H2 plus O2, they're separating it out, and so they can run it and use that 1.23 volts that comes out of it to do useful things. And that's great. That's a wonderful thing. However, right now, the issue is, how do you split that water? Well, you have to use energy. In fact, you have to use quite a lot of energy, right? Because you got to make that other voltage to push against it. Where do you get that energy from? Well, in the US, mostly that's still from burning fossil fuels. So, right, instead of burning fossil fuels in the car, you burn fossil fuels somewhere else, right? There's a problem with that, right? You're still burning the fossil fuels. Now, hopefully in the future, we can continue to develop all these alternative energy sources, and we can split water, make fuel cells, and then have things that use that energy that's still not burning fossil fuels. Okay, so water electrolysis is the world going backwards. And there we go. So we have our 2H2O liquid going to 2H2 gas plus O2 gas. And like I said, we've got this driving force of 1.23 volts in this direction. And what we're going to do is we're going to put a larger driving force, I'm just going to make a number, of 5 volts in that direction. Why 5 volts? Because I did, right? I could say 10 volts. I could say 100 volts. I could say whatever. I just need a larger driving force going against it than I need going for it. Where do we get that potential? We can use a different battery. We can use a power supply that you can get in a thing, right? You take these little wall warts right here that you plug in your USB to, and that's 5 volts right there. So you could theoretically do it using that. Okay, so all sorts of ways of getting that. Okay, so that is our water electrolysis. We're now going to force the reaction to go this direction. We're going to create O2 and H2. Now, if we were in person, one of the things I would do is a demo of electrolysis, because it's really neat. If when you set this up, the stoichiometry says I should make twice as much hydrogen as I do oxygen, and you set up this electrolysis apparatus, you capture hydrogen on one side, you capture oxygen on the other, and you can visually see that the hydrogen side is about twice as much gas displacing water on that side as it is on that side, so it's kind of fun. So That's electrolysis. What does it look like? It looks almost exactly like a galvanic cell, right? You've got one thing on one side, one thing on the other side, but instead of measuring a voltage and having your current go in the natural direction, you are now providing a voltage source. So there's in this case, we're talking about zinc and copper. There's a 1.1 volt driving force in this direction, and what we need to do is we need to provide a source that's greater than 1.1 volts to force the electrons to go in the direction that they don't want to go. Notice the electrons in this one are moving off to the right. The electrons in this one are moving off to the left. And so we're forcing the electrons to go opposite of where they would like to go spontaneously. And so what does that do? That makes it so that instead of the natural thing of zinc being oxidized when you put it with copper, we're now reducing zinc when it's with copper, because we're forcing the opposite thing to happen. What I want you to pay attention to is a little bit about the structure of this, is that electrons are now going the opposite direction because we're forcing them to, right, by providing this extra potential above and beyond the cell potential of the system. And we're now doing the opposite reaction. So instead of zinc being oxidized naturally, it's now being unnaturally reduced. But look at the language here. Because zinc is now being reduced, it's the cathode. It was the anode because that's where oxidation was taking place. So the language stays the same in an electrolytic versus galvanic cell. The cathode is where reduction takes place. The anode is where oxidation takes place. And so they actually end up switching. And so in an electrolytic cell, you'll often see people write it and draw it where the cathode's on the left and the anode's on the right. So it's consistent with the galvanic cell, not where the cathode and anode are, but where the natural cathode and the natural anode are. Is it required to do that way? No. And we're not going to do line notation for electrolytic cells, so you don't have to worry about that one either. Okay. So we switch off who's the cathode and who's the anode. We switch who's being oxidized and who's being reduced. And we have to make sure to provide that potential. But other than that, the system looks pretty much the same. Okay, overvoltage. Why it doesn't work even though it should. So here's a picture of an electrolysis setup for water. They just took a big giant battery here, hooked it up to some wires, and you can see very clearly that there's about twice as much hydrogen produced as oxygen in these little test tubes, and you can see the gases coming off of the electrodes down here. But, right, this is a 1.23 volt system. So it's pushing with 1.23 volts to make hydrogen and oxygen to make water. So you think, okay, well, what if I just pushed it with 1.24 volts in the opposite direction? Would it work? And the answer is no, right? You're like, okay, that was pretty small. How about if I do 1.5 volts in the opposite direction? Would it work? That's a decent amount of extra voltage. And right, 1.5 volts is also the voltage of a AA or AAA battery. So you're like, let me take a AA, AAA battery, hook it up to this system, and see if it works, and nothing happens. So why is nothing happen? Why are we saying, hey, let's take these things, let's put in more voltage than need be, and still nothing's happening? In fact, we would have to get to, what did I do? About 1.7 volts or higher for this thing to work. Why? Because it's something called overvoltage. Now, overvoltage is literally just a fancy term for activation energy. Right? If we draw our little reaction coordinate diagram, our normal reaction is this. We've got H2 and O2 going to H2O. Right? And there's a small activation barrier going the forward direction in an exothermic reaction. This one's pretty spontaneous, so it's a relatively small barrier. It's not zero, but it's relatively small. But one thing moving forward is enough to make energy for everybody else to go. But going backwards, we don't just go to this 1.23 volts of energy. We have to go above that 1.23 volts of energy. And it just turns out the number happens to be that we need to go about 1.7 volts or higher. So even in electrolytic cells, you can't just provide greater than 1.1 volts like we said on the last slide. You actually have to provide something over that, and how much just depends on the activation energy. We're not going to calculate any of that. We're not going to quantify any of that. You don't need to be able to say like, oh, in the zinc and tin case, the overvoltage is going to be 0.74. No, you don't need to know any of that. But you do need to understand what overvoltage is and why it applies to electrolysis reactions, and it's just activation energy. But the consequence of it is also important, which is you always end up needing to apply more voltage than the calculated standard cell potential. All right, electrolysis, how fast is it? Okay, let's do an electrolysis reaction where we're turning zinc 2+ and we're turning it into zinc solid. Doesn't really matter what we're doing it against for the purposes of this calculations. And let's do 1 mole of zinc at a current of 1.0 milliamps. Now, if you remember, an amp is a coulomb per second. Milli is just 10 to the minus third. So we have about 10 to the minus third coulombs per second. Why did I pick that number? That's a reasonable and normal current to come out of like a little AA battery if you're running something, a milliamp of current. Pretty common, and you can do that well. So that's going to be 0.0010 amps, or 0.0010 coulombs per second. Okay. Now, if you look at here, 1 mole of zinc requires 2 moles of electrons. You can see that from the stoichiometry here, right? This is just our N in our other equations. But we have to calculate that because if we're talking about coulombs per second, what is that? That's electrons, right? That's not zinc, that's electrons. And so we always have to convert to moles of electrons when we're doing calculations of time or other things with electrolysis. Now, what do we know about 2 moles of electrons? 2 moles of electrons, 96,485 coulombs per mole. That's Faraday's constant. Faraday's constant tells us how many coulombs per mole. Why am I trying to get to coulombs? Because my current has coulombs and seconds in it. I'm trying to find seconds. I need to find something to get rid of those coulombs. So if I do that one, my moles cancel out and I get 193,000 coulombs. And what do I find here? I've got 193,000 coulombs times 1 second over 0.0010 coulombs, right? That's my current. I multiply that out, and I get 1.9 times 10 to the 8th seconds, which is about 6 years. Wow. So if you wanted to plate a mole of zinc, right? A mole of zinc isn't a whole lot of zinc. I don't remember what the molar mass of zinc is, but you're talking, 60-ish grams of zinc. If you did it using a AA battery, and obviously you'd have to switch out your AA batteries over time because most AA's don't last 6 years, it would take you 6 years to do it. Wow, that is a slow process. And so what you find is that most people don't do it using 0.001 amps. They don't use it using milliamps. If you're trying to electrolyze things, you generally tend to use very, very large currents to get down that number. Now, using very large currents is dangerous because current is what kills. Voltage doesn't kill. If I get 1 electron at 10,000 volts, I'm not going to feel it. But if I get, coulombs and coulombs of electrons at 1 volt, it's enough to kill me. Okay, so it's the current that kills you, not the voltage. So using a large current is necessary, but it does make the process a little more dangerous, which is why you want to make sure that you know what you're doing before you try electrolysis. All right, so 6 years in order to do that at 1 milliamp, right? If you turn that to 10 milliamps, it would be 0.6 years. 100 milliamps would be 0.06 years. 1,000 milliamps or 1 amp would be 0.006 years. Much more reasonable. 10 to the 4th seconds, thousands of seconds. You can do that quickly. Now, the problem with electrolysis, if you do it too fast, you start to have other problems, other reactions that happen. So there's a balance about speed on these things. Notice I didn't have a very fixed formula that I used. Oh, you just plug it into this formula. I kind of just made the units work. And I know that's going to be rough on some of you who really love to have formulas. I just need to know how to get from A to B to C by plugging into my formula. But these problems come in a variety of flavors. And so I really want you to just be able to kind of play with the units, knowing that you have to use moles of electrons, knowing that current is coulombs per second, knowing Faraday's constant is coulombs per mole, and relating all of these things to one another. Could I bundle it up as an equation? I'm sure I could, and I'm sure if you look on the internet, somebody has. But what I actually prefer is you think about it and try to manipulate these things in the right way to get the right answer. Why? Because it's a useful exercise. This is a not too difficult situation to try that exercise in. All right, your turn. What current in amps would be required to electroplate 1.00 grams of gold from a 0.1 molar gold 3+ solution in 1 hour? So I want 1 gram of gold in 1 hour. And it's very interesting. Most people don't know there's a ridiculous amount of gold in the oceans. Huge, huge, huge amounts of gold dissolved in the oceans. But we have a couple problems. One, it's a relatively low concentration in any particular spot. And two, it's a very expensive process to extract it. But if anyone ever figured out a way of doing it energetically efficiently, they'd be very rich because there's tons and tons of gold in the oceans. All right, so your turn to try this one and go. Okay, see you. All right, there we go. 1 gram of gold. Well, what do we know? We know that all this stuff occurs in units of moles. We know that amps is coulombs per second. So first thing I want to do is I want to convert that grams of gold to moles of gold. And that's going to be 100 and... Oh, forgot to turn my page here. Oh no. Oh no, there it is. 196.97 grams of gold, and you get 0.005077 moles of gold. All right, now, how does that help us? Well, we don't want moles of gold, right? We want moles of electrons, because we know all this stuff is occurring in moles of electrons. 0.005077 moles of AU. How do I convert that to moles of electrons? Well, if I've got gold 3+, if I'm trying to convert that into solid gold, that's got to be 3 moles V minus for 1 mole of gold. So you can use the charge there to help you figure that out. And that's going to be 0.01523 moles of electrons. So I'm closer now. I've got moles of electrons. But I want moles, right? An amp is a coulomb per second. How do I relate moles of electrons to coulombs? Coulombs per mole. What thing has coulomb? Oh yeah, 96,485 Faraday's constant. And so I get my coulombs over here, which is going to be 1469.8 coulombs. Right? 1 hour is 3,600 seconds. An amp is a coulomb per second, so I'm just going to take my 1469.8 coulombs divided by my 3,600 seconds, and what do I get? 0.408 amps. 408 milliamps is the current that I need in order to electroplate 1 gram of gold in 1 hour. It's not a whole lot of gold, about a half an amp, a little under half an amp, which is a moderate amount of current in order to electroplate that. All right, that was it for this video, which we talked about electrolysis, which is simply the way of making the world run backwards, where reactions that are normally spontaneous, we can reverse them, and we do the non-spontaneous version by putting an outside force in that pushes against it and forces it to go in one direction. And we've seen that before too when we talked about the human organic creation that we are. We are made up of a bunch of smaller molecules combined to this larger organism, which defies entropy apparently. But what we do is we pair that with reactions that are very, very favorable, metabolism reactions and other things like that, we release a ton of heat into the universe. And it's the combination of those that makes this seemingly non-spontaneous thing spontaneous. Same thing for electrolysis. Normally looks non-spontaneous. We pair it with something else that turns it into spontaneous. And it doesn't sound spontaneous because you're having to force it. But remember, anything that happens is technically spontaneous when we look at the entire system. So the fact that the electrolysis is happening means it's spontaneous when we look at the reaction plus the thing we're putting in. Right? It's non-spontaneous if we're just looking at the reaction, but it's spontaneous if we took the reaction and the thing we're driving it against. All right, thanks so much for listening. Have a wonderful day.